All right, this is a continuation of what we did last time, but in this section we talk about areas of surfaces of revolution. Last time we talked about the volume of revolution. The difference is pretty much it's either the meat of the subject or the skin. Oh, let me get my figures. There. And so we're going to get the areas of the surfaces. And unlike last time, if we had a curve in a closed interval and we rotated it about the x-axis, then we got this cylinder. Now we just want to know what is the surface area of this object. Kind of like the example of the book. Whenever you jump rope, the jump rope itself makes this surface area that you jump inside. You jump inside. So, and that's what we're going to look for the cocoon around there. Let's begin by looking at the simple surfaces. We had a horizontal line. There's a point A and a point B. And it's bounded by x1, x2. Again, if we create a revolution about the x-axis, if we're revolving around the x-axis, we'll get a cone, a tube, because all we have, remember, we start off with this straight line. The circumference of this tube since it's rotated, it's 2 pi times the height, or whatever the radius is. Because the radius is equal to y. So it's 2 pi r. Since y equals r, we have this. The surface area of this object would be the circumference times delta x. So it's going to be 2 pi y delta x. That is our surface area for this object. Pretty straightforward. That's how much material you need to wrap around this hose or this tube. So horizontal lines are pretty easy. But as I say, it's not always going to be that easy. So now let's look at the same one, but this time with a slant. And if we rotate about the x-axis, What this is called a frustum of a cone. If it was the entire cone, it'd be like that. But we're just taking a small section of it. So it's called the frustrum of the cone. We're only looking for a small part of it. So the area of this curve, remember, there's our radius, but it changes. So to find the area of this, what do we have to do? We have to have a whole bunch of these small slivers because the y changes. So we're going to have the product of those. What this represents, though, is these small ones this is x1, this is x2, and on our curve, if we were to blow up a small part of the curve, it would look like this. So this would be y1, this would be y2. What we're looking for here, since we have the slant, we're not going to get an accurate picture. The only way we get an accurate picture is if we take the average of these two y values. So y1 plus y2 divided by 2, and we multiply all those together. And the line connecting point 1 L is the line connecting A to B. This is point A and this is point B. So we're looking for the average heights of all these because it is decreasing in altitude. So what we're looking for here now for our surface area we're going to have, again, it's a rotation, so it's 2 pi times our height times the width, L, which is the length between them. But we know we figured out that we can't use it because it's an average. So this triangle is going to make up for the triangle that we're missing there. So our y sub n becomes y1 plus y2 over 2 divided by L. The 2's cancel. So we have our surface area now becomes y1 plus y2 times L. We're building up our pieces of our equation the same as we did last time. So now let's define what we have for L and what we have for y1, y2 with respect to x. Because eventually, remember, we're trying to get to adding up all the segments and think the limits. We have to try to make this go into the Riemann sums. So we have to make these into functions of x. Let me just write that one down. So we have s of a equals pi y1 plus y2 times L. And remember, we had our curve. And this point here is the y1 plus y2 divided by 2. The length, L, is the length connecting our 2 points. So let's look at the stuff. Y1 with respect to x would be f of x1 plus y2 is f of x2. Now, how do we define L? Since it's not a horizontal line, we have a slant. What's the formula for L? Remember, it's the distance from this point to this point. X1, Y1, and that point is X2, Y2. So L is the distance, so we use Pythagorean theorem. So L squared is equal to delta X squared plus delta Y squared. X2 minus X1, Y2. So it's the square root of delta X squared, delta Y squared. So our surface area formula now becomes f of x1 plus f of x2 times the square root of delta x squared times delta y squared. So this would be the formula to find the surface area of this small segment rotated. But we have a larger segment, so we have all these x1, x2, all the way to xn. So we have all these are x sub k's. And besides that, remember our summation, we dealt with k equals 1 to n. So we have to make all of these functions. So this is x k minus 1 plus f of xk. So if k is 1, or if k is 2, then it's 1 plus 2. Same thing with the delta. Delta xk squared, delta y sub k squared. So that is our formula for our surface area. And it works even if we have a curve. Remember, we started off with a slant. works even if we have our if f of x is a curve. In other words, if we want to know this surface area between this point and that point, between A and B. Well, A and B were the line. Oh, that's great. Because the x values are still xk minus 1, and this one's x sub k. So the distance between there is delta x sub k. This is y sub k minus 1, and this point is y sub k. So this is delta y sub k. Because that's that point there. This is xk, yk. This is x sub k minus 1, y sub k minus 1. We would still draw a line. This is line L, connecting points A and B, because it would still create a right triangle. So we can use Pythagorean theorem. So L would still equal delta x sub k squared times or plus delta y sub k squared, the square root of that. And yes, you notice there's a little space between that line and the curve. How do we fix that? How do we account for this space that's between the line and the curve? Well, yeah, because if we could make these delta x's go to 0, in other words, if we increase the number of subdivisions, partitions, we make that area above the line smaller and smaller and smaller and smaller. Eventually, as our delta x goes to 0, we have the actual curve of the line. So the frustum, that's this area, the sum of frustum area equals, those of you came in, if we have a cone and we just took a small part of it, if we only took this part of it, that's called a frustum. So the sum of the frustum area, the formula for this would be the summation as k goes from 1 to n pi f of x k minus 1 plus f of x sub k times the square root of delta x sub k squared plus delta y sub k squared. So as you see, we're getting closer and closer and closer to our Riemann sum. So now we have, in order to find the limit, we have to make sure that first off, the function is differentiable. Because we have to find our first derivative. We will have to find f prime. Because what is this going to find for us? We're looking for surface area. So we have to figure out where the tangent line is, so we can figure out now as we start going down and down and down, we can get the actual summation of all those to get the surface area. All right, so we have delta y, delta x. So how would we define why do we use, instead of x, why do we use c sub k? Because as we look at our endpoints here, remember, this is delta x. As delta x gets smaller, this gets smaller. But by the mean value theorem, there has to be a point C between x sub k minus 1 and x sub k. There has to be a point C that's halfway between x sub k minus 1, x sub k. Again, we use that because the area above and area below this line L is going to wash itself out. So this is our f c sub k. We find the derivative of it to find the tangent line to it. Its formula is delta y sub k over delta x sub k. Remember, inside here, we're trying to figure out what delta y sub k is. Because if we can get it all into, because this equation here is already a function of x. Now we have to figure out this one. So we know that f prime is delta y sub k over delta x sub k. Solve for delta y sub k. Multiply delta x sub k to both sides. And there we have our relationship to delta y and our function with respect to x. So now substitute this back into the equation. We have delta x sub k squared plus delta y sub k squared. So I plug what we just found into there. And we found that. So it becomes xk minus 1 plus f of x sub k delta x sub k squared plus, now delta y is f prime of c sub k delta x sub k squared. If we look inside here, since this is a product, we can distribute both of those. We have delta x sub k squared plus f prime c sub k squared delta x sub k squared. Now you notice each of our terms inside the radical are all in with respect to sub k, not k minus 1, but just k. Now inside here, we can factor out a delta x sub k squared. That's pi. F of k minus 1 we factor out a delta x sub k squared out of both of those. Since it's a product, I could make both of these into actual their own square roots. Cool. So what we have right now, because we're getting very close, f of x k minus 1 f of x sub k 1 plus f prime c sub k squared times delta x sub k. Again, that's all algebra. Now we take the limit of both sides as delta x goes to 0. As delta x goes to 0, we get Riemann sum, which is the limit. We get my example sheets. We're getting close to an example. So this is our integral, defining the surface area of a rotation. Because last time we found the volume inside this rotation. Now we're just looking for the surface area. Can you think of an example, a real world example of where this would be used? Why would you care about the surface area of a rotated body? The what? Well, yeah. For example, this is think of spaceships, like the shuttlecraft. They had to know how many of those tiles to put on there. Each of those tiles are expensive. They had to make them by hand. And so you figure out what is the surface area of this object. You did it by pieces, and then you figure out each piece now takes care of this surface area. How many do we need for this entire shuttlecraft? So this will help us figure that stuff out. Or if you want to put a heating element on top of a pipe, how much material do you need? So what's that? Because as here's our summation. As we take the limit as delta x goes to 0 of this function, what's really happening now is, remember, we're taking a rotation around the 2 pi. The function is that, and this whole area here is that. Well, this area, I should say. The dx is what we're taking respect to. So we have the rotation, we have the height, we have height times width. Here's the height, which is both of those, because originally it was divided by 2, because we had 2 endpoints, we had a slanted curve. So we're looking at just the surface area, I mean the height of this object. The width. The width is the length between point A and point B. let me the line connecting point A to point B, that's what L is. So in essence, it deals with our width. So here we have the height, the width, and we're rotating around 2 pi with respect to the x variable. Because we're rotating around the x-axis. If we rotate around the y-axis, we'd have it dy. So let's put all this stuff together with a formal definition. Area of a surface of rotation. This is what we're going to define. Let f of x be a continuous and differentiable function on our closed interval AB the area of the surface of rotation of the graph. Since we're dealing with now with the x-axis, so since we're dealing with dx, we're doing the x-axis, is this. That f be a function that is continuous and differentiable on a closed interval. The area surface rotation of the surface area of this graph about the x-axis is given by surface area, or S, the integral of a to b of 2 pi f of x times 1 plus f prime of x squared dx. Look familiar? Last section we had the same type of formula. All right, let's look at an example. Find the area of the surface generated by revolving the curve y equals 2 radical x from A to B. A is 1, B is 2, about the x-axis. So if we just look at it from xy standpoint, we're looking for this surface area rotated. Okay, so how do we do it? Since we're looking for the area of the surface rotated, then we know we have to use this formula. and rotate it around the x-axis. F of x is 2 radical x. So we have to find what? The first derivative. So what is the first derivative of 2 radical x? We have to first convert this into that. So we have 2, that's a constant, leave that in front. Bring down the exponent and subtract 1. So 1/2 minus 1 is negative 1/2. So the 2's cancel. We have 1 over radical x. That's our first derivative. Surface, it goes from A is 1, B is 2. 2 pi times 2 radical x times 1 plus 1 over radical x squared dx. I would just plug them in there. The integral from 1 to 2. 2 times 2 is 4 pi radical x. One over radical x becomes 1 over x. And we squared it. We square the top and the bottom. So let's just remember, last time we had to figure this one out. So we'll come over here. 1 plus 1 over x. That is, get a common denominator, x plus 1 over x. Four pi. That's 4 pi radical x times radical x plus 1 over radical x dx. The radical x's cancel. So we have 4 pi 1 to 2 of radical x plus 1 dx. So this becomes 4 pi x plus 1 to the power 1/2 x plus 1, add 1 to the exponent, 3/2 and divide by 3/2. From 1 to 2. This is 4 pi. This 3/2 becomes 2/3. X plus 1 to the 3/2 power from 1 to 2. Two times 4 is 8 pi over 3. So I have 2 plus 1 to the 3/2 minus 1 plus 1 to the 3/2. So this is 1 1/2. This is 1 1/2. Which is 3 radical 3 minus 2 radical 2. Whatever that gives us, that'll be the answer. Any question about that one? Okay. Then last part of this section is revolutions about the y-axis. Because we did the same thing last time. This is about the y-axis. We have 2 pi. Now, instead of the height, we're looking at the width. That's 2 pi x. 1 plus dx dy squared dy. Because remember, if we differentiated with respect to x, it would be dy dx. That equals y prime. But now we're doing dx dy. We're looking for x prime. That's what that is. C to d, 2 pi g of x, or g of y, not g of x. 1 plus g prime of y squared dy. This is the rotation with respect to the y-axis. This is not a g, it's a y. Ready for an example? Let's finish up the chapter. So this one? The line segment x equals 1 minus y from 0 to 1 is revolved about the y-axis to generate a cone below. Find the lateral surface areas, which excludes the base area. So we want to know this surface area. So the lateral surface area is the base circumference divided by 2 times the height. And the height is this slant. So what that equals okay. So what do we have? We have what's our C, what's our D? It's going from 0 to 1. Our g of y, which is our x function, is 1 minus y. So the derivative of this, so x prime, is -1. Notice it's not a related rates problem. When we take a derivative of y, we don't have to put dy dx behind it because we're changing the order of integration. So now plug in all of this stuff into our formula. The surface area is from C to D, 2 pi x, 1 plus g prime of x squared, not x, y. Gy. So it's going from 0 to 1 to our x. X is equal to 1 minus y. Times 1 plus our g prime, which is -1 squared. Dy. Okay. From 0 to 1, 2 pi 1 minus y. This becomes a positive 1, so it's radical 2. Okay. So then integrate this with respect to y. So we have 2 radical 2 pi We're integrating from 1 minus y dy. Two radical 2 pi. The integral of 1 is what? Yeah, so what integral of 1 would be y? It would be x, yes. Normally it'd be x, but since we're integrating horizontally. And the integral of y squared over 2 from 0 to 1. So we have 2 radical 2 pi, 1 minus 1/2 minus 0, since it's to 0. 2 radical 2 pi, 1 minus 1/2 is 1/2. The 2's cancel. Radical 2 pi is our answer. That's the surface area. That's it. That finishes chapter 6 for us. Only 4 sections. I know, it's so sad. But almost all the formulas are the same in chapter 6. If you look at them, they're almost all identical. Because they all deal with rotation. So you have a 2 pi. Do you take the surface area or do you take the whole function itself? And that's what this part is. This part is always the same. It's always the square root of 1 plus f prime squared, or 1 plus g prime gy squared. So the only thing different is, do we take just the surface area or do we take the whole volume? Okay, that's it. So try to do your homework this weekend. And okay, I'm gonna go and scan everything and try to get sent out to you today. And we will start chapter 7 on Tuesday. It didn't record.